Okay, ladies and gentlemen, good day all. Today we are going to look at the specific heat capacity, starting with heat capacity. So what is heat capacity? Heat capacity is actually represented with capital letter H, indicating that is the amount of heat, which is Q, that is required to rise the temperature of a body by 1 degree centigrade or Kelvin. It means that let's say you have a body and this body A, maybe actually the mass of this body or the temperature of this body is 32 degrees centigrade. So the amount of heat that is required to increase this temperature from 32 degrees centigrade to 33 degrees centigrade is what we call heat capacity. So the amount of heat that is required or that is needed to increase the temperature of a body by either 1 degree Celsius or 1 degree Kelvin is what we call heat capacity. And this heat capacity, it has a unit, and the unit is joule per Kelvin or joule per degree Celsius. Although we know that this is the quantity of heat, the quantity of heat is like an energy, so it measures in joule, while the temperature is measured. This is delta T. So delta T, it means change in temperature. The delta T here means change in temperature. So the change in temperature is the same thing as T2 minus theta 1. So T2 is a final temperature. T2 is a final temperature. T2 is final temperature, while T1 is an initial temperature. So T1 is initial temperature. It's initial temperature. So, and the SI unit of temperature, we all know that it is either degree Celsius or Kelvin, or it can be even Rankine or Fahrenheit. All these are SI unit for temperature. It can be degree Celsius, Kelvin, Rankine, or degree Fahrenheit. All these are SI units of temperature. And this is change in temperature, which is delta 2 minus delta 1. The the theta 2 is the final temperature, while T1 is an initial temperature. And generally, the temperature is either you measure it in degree Celsius or Kelvin. And that is where we have degree joule per Kelvin as an SI unit of calculating the heat capacity, and it's represented with capital letter H. And Q means the energy, sorry, the amount of heat, that is the quantity of heat. So now the next thing that we are going to look at is specific heat capacity. So specific capacity is like a heat capacity, but the only thing here, there is a specification in terms of the mass. So since a body with different masses require different quantity of heat, that require different quantity of heat to rise the temperature to 1 Kelvin, so we need to specify the heat capacity. So in a specific heat capacity, because of course we have, or different substances have different masses, and the masses also affects the number of temperature or the amount of heat that is needed to increase the temperature of that particular substances. So that is why we need to specify. We need to specify the mass. So in a specification, that is a specific capacity, it means that it's a quantity of heat that is needed or that is required to rise the temperature of 1 kilogram of mass of a substance by 1 degree centigrade, or by Kelvin, by 1 Kelvin. So it means that in a specific capacity, you have a specific mass of a substance. But in the case of heat capacity, there is no specification. There is no specification because different substances have different masses. So therefore, the quantity that will be needed to raise their temperature may also be varied. So that is why in the case of specific capacity, we have to specify it. We have to specify it. So in a specific capacity, we are talking about the increase in a temperature or the amount of heat that is needed to increase the temperature of a body or of 1 kilogram of a substance by 1 degree centigrade or Kelvin. So it means that the specification here is the mass. And we have a formula for calculating this specific heat capacity. Remember that in heat capacity, we said that heat capacity is equal to Q all over delta T. So, but in the case of specific capacity, we have a specific mass. So as a result of that, the specific capacity is now written as Q all over M delta T, where M stands for the mass of the substance, delta T here stands for the change in temperature of the material, and then the C here stand for the specific heat capacity. So of course, remember that from the previous slides, we said that the SI unit of heat capacity is joule per degree centigrade. But in this case, we have mass. So we can now say joule all over. The mass is kilogram, is kg, is kilogram, and then we have the temperature in degrees centigrade. So that is why the SI unit is written as joule per kilogram per Kelvin as an SI unit of specific heat capacity. So I think, ladies and gentlemen, this one is clear. We can see that the specific heat capacity and heat capacity is just that the difference in the case of specific heat capacity, we specify the mass, while in the heat capacity, there is no specification of the mass. And that is what actually brought the differences between the two uh, parameters. Okay, so now the next thing that we are going to look at is a simple calculation. The question says calculate the quantity of heat absorbed by 50 grams of a solid copper when its temperature increases from 25 degrees centigrade to 250 degrees centigrade, and the specific capacity of copper is equal to 380 joule per kilogram per Kelvin. So I think by looking at these questions, we can see that it's simple. So this is the mass, and we usually calculate mass in kilogram. So we can now set mass of a copper, that is MC, is equal to 50 gram. So if we have a mass in gram, we have to convert it to kilogram. So how do you convert mass to gram to kilogram? We divide it by 1,000. So if we divide 50 divided by 1,000, then at the end, we are going to have 0.005. I'm going to have 0.05. Yes, 0.05. So we have 0.05 kilogram. So we convert this to kilogram. And of course, we have the change in temperature, which is the temperature increase from 25 to 250. So it means that our T1, that is initial temperature, is 25 degree centigrade. It's 25 degree centigrade, while the final temperature, which is theta2, is equal to 250 degree centigrade. So therefore now we are going to calculate delta T, that is the change in temperature. So the change in temperature is equal to theta2 minus theta1. And our theta2 is equal to 250 degrees centigrade minus 25 degree centigrade. Therefore, at the end, we are going to have 225 degree centigrade. So, and then now we have this, and of course our specific capacity of copper, that is CC, the specific capacity of copper is equal to 380 joule per kilogram, per Kelvin. So now what do we do? Then we now write the formula. The formula is Q is equal to MC delta theta or delta T, not theta, delta T. So our M is 0.05, which is the mass, and our C, which is specific capacity, is 380 times our change in temperature is 225 degrees Celsius. So therefore now at the end, we are now going to calculate this. We now have 0.05 times 380 times 225. Then at the end, we now have 4,275, because it is Q, that is quantity of heat, then the SI unit will be in joule. So this is the answer for these questions. I think it is very clear. First, we are given the mass in grams, so we have to convert it, because usually in physics, we don't calculate mass in grams, so we have to convert it. So we convert it to kilogram by dividing the gram by 1,000. And then we have the change in temperature from 25 to 35. So we have to calculate our delta T, that's the change in temperature. And the change in temperature is delta 2 minus theta, or T2 minus T1. And then we now have 250 minus 25. Then at the end, we have 225 degrees centigrade. And now we have our formula which says Q is equal to MC delta T. And then our mass is 0.05 times 380 times 225. Then we have 4,275 joule. That is how we obtain our mass. So now the next thing that we are going to look at is the measurement of specific heat capacity. So in this case, we are going to measure the specific capacity using a method of mixture. So in this method is actually, we are going to apply the law of conservation of energy. And this law is actually considered when you have a hot substance and mix it with cool substance, provided that there is no extent or there is no loss of energy from the system to the surrounding, then the heat loss by a hot body is equal to the heat gain by a cool body. So this law is actually, or is usually applied when you have an isolated system. Remember that when you said an isolated system is a system where there is no loss of energy or substances between the system and the surrounding, between the system and the surrounding. So it means that in this case, this law is applied when we are talking about that, or when we are actually looking at this from the point of there is no actually heat that lost between the system and the surrounding. So it means that in this case, you have to work with an isolated system. You have to work with an isolated system. Why do you need isolated system? It's because, number one, if you have a substance here that is hot and the system is not isolated, of course, some amount of heat will be lost to the surrounding. So therefore, as a result of that, the amount of heat that is lost by the hot substance is not equals to be the amount of heat that will be gained by the cold body. So as a result of that, we have to work with an isolated system. So if you have an isolated system and you now have a hot object and you place it inside that isolated system, then what will happen? So let's say you have a hot object, and you now transfer it into a cooled water, in an isolated environment, then the hot object will be losing heat. So as the hot object is losing the heat, then the cool object, which is the water, will be gaining heat. And that is the law of the conservation of energy, provided that you have an isolated system And then you now transfer a hot object into a cooled environment, maybe in a water, in an isolated medium, then uh, the hot object will be losing heat, while the cooled object will be gaining heat. So as a result of that, we are now going to have this formula. Remember that we said specific heat capacity is equal to Q is equal to MC delta theta. So in this case, we have QH. It means that is the quantity of heat of the hot object. MH is the mass of the hot object, CH is the specific capacity of the hot object, while TH is the temperature of the hot object, while T is the temperature of the mixture, So now then the next thing is we also have a formula where we have QC, MC is equal to CC. QC, it means the quantity of heat of the cold object. MC is the mass of the cold object. Then CC is the specific capacity of the cold object, while T is the temperature of the mixture, and then TC is the temperature of the cooled object. So I think the most important things that we need to understand at this point is actually this change in temperature. Usually in the case of hot objects, we take the temperature of the hot object subtracted by the temperature of the mixture, which is T. And then in the case of the cooled object, we take the temperature of the mixture and we subtract it with the temperature of the cooled object. Okay, now let's take this example. Let's say we have a container, and in this container, we have a cooled water, and the temperature of this cooled water is, let's say, 20 degrees centigrade. Then now, you now transfer a hot object, and this hot object is having a temperature of, let's say, 70 degrees centigrade. So this 70 degrees centigrade is the temperature of the hot object. And this 20 degrees centigrade, this 20 degrees centigrade is the temperature of the cooled object. So it means that TC will be the temperature of the cold body, and then TH will be the temperature of the hot objects. So now, if you now mix these two objects together, the hot and the cold object, what will happen? The temperature of the hot object will be decreasing, and at the same time, the temperature of the cold body will be increasing. Then they will now reach a temperature called temperature of the mixture. So maybe at the end, after this mixture, after the mixed and all the transfer of heat from hot and the hot objects is being completed, then what will happen? The temperature may actually maybe increase for all the two. The temperature of the whole object and the cooled object after the mixture will be maybe something, let's say it's an assumption, let's say around, let's say 45 degrees centigrade. So it means that after the mixture, the hot object loses its temperature, loses about 25 degrees centigrade, and then the cooled object gets a temperature of about 25 degrees centigrade. So this is the temperature of the mixture. So that is why if you actually going to use the law of the conservation of energy, you are now going to set the heat lost by the hot object is equal to the heat gain by the cooled objects. So what will happen? So always, if you want to, the temperature of the cooled object, the temperature of the cooled object will now be the temperature of the mixture. That is the increase in temperature in the case of cooled object will be the temperature of the mixture minus the temperature of the cooled body. That is before adding the hot object. And of course, in the case of the temperature of the hot object, it will now be the temperature of hot object minus the temperature of the cooled object. That is how we are going to calculate the change in temperature in the case of the hot material. So therefore, at the end, we are going to have this formula MC CH TH minus T is equal to MC CC E minus TC. Okay, so ladies and gentlemen, I'm going to stop here for this video and I'm going to look at examples under this. Okay. Thank you.